In the next example, we're going to use these two properties to help us solve for limits of sine and cosine. So if I can get sine to have a matching theta like this, then it'll equal 1. If I can get cosine to have a matching theta, if it's cosine minus 1, it'll equal 0. So looking at this example right here, what we're going to do is use the sine formula, or the sine property, and get a matching theta. In this case, the theta is a 7x. So we want to get a 7x on the bottom. So what I'm going to do is take the 7x and multiply by 1 over 7x on top and on bottom. Since I'm doing this on top and on bottom, the fraction is still balanced. So I'm going to rewrite this as sine 7x over 7x divided by 4x over 7x. Now this property is what we just saw. The limit as x approaches 0 for this is 1. And then down here, the x's reduce, so you have 1 over 4/7. And then you have 1 divided by 4/7, which is 7/4, the reciprocal. So that would be the answer. Here we've got the limit of x times cotangent x, and what we're going to do is change this into cosine over sine to begin with. So let's start there. And so what we can do is, you've got x over sine x. What we can do is get x on the bottom of this sine x if we multiply top and bottom by 1 over x. So on top, this x and 1 over x cancel. So we have cosine x over sine x over x. This, when we plug in our limit, equals 1, according to the property. And then this, when we plug in the limit, equals cosine of 1, or cosine of 0, sorry, which is 1. If you look at your unit circle, the cosine of at 0 is 1. So you've got 1 over 1, which is 1. Final answer. Simple harmonic motion, example 3. An object at the end of a vertical spring is stretched 4 centimeters beyond its rest position and released at time t equals 0. If position at time t is s equals f of t equals 4 cosine t, find the velocity and acceleration at time t and use them to analyze the motion of the object. So we've got a position function. What we're going to do is find the first derivative for the velocity and find the second derivative for the acceleration and use them to analyze the motion of the object. So your original function in red is 4 cosine x. Your derivative, your first derivative, you would leave the 4, and then derivative of cosine is negative sine x. So that'll be in blue. Then in that negative, you can go ahead and put in front if you want to move it in front. So then you've got a negative 4 in front, which you leave, and then derivative of the sine is cosine. So the red is your original, the blue is your velocity, and green is the acceleration. And so what we can see is when we follow the red, its position at time 0, it's pulled 4 centimeters from its its equilibrium position. So we can see that it's pulled 4 centimeters away, and as time goes on, it reaches equilibrium, and it contracts the other way, and then back to equilibrium, and then extends again, back to equilibrium, and then it scrunches and back to equilibrium and extends. So the red is showing what a spring would be doing if, I guess assuming there's no gravity, and it would continue to go back to its original extension. And then remember, the blue was the velocity. So we can see at its full extension, it has 0 velocity. And at equilibrium, it's got its biggest velocity. When it is fully crunched, it's got 0 velocity again, and then here when it hits equilibrium, it's got its highest velocity. So that's something we could see. And then looking at the green, the acceleration function, we see when it's fully extended, it's got its highest acceleration. When it's at equilibrium, it's got zero acceleration, and so on.